Can you hear me? Yeah, you can. Good morning, everyone. Welcome to the final session of this conference. The first talk is about lattice-based zero-knowledge proofs for blockchain confidential transactions by Shangao, Tianyu Zheng, Yu Guo, Zepeng, and Bin Zhao. And Tianyu is going to give the talk.
How to use this pointer? Okay.
Turn it on. Okay, so this left and right.
Okay. Okay, thank you. Hello, everyone. My name is Tianyu Zheng, and it is a great honor to be here to introduce our work. So this is a joint work, as the author listed. So at the beginning, I would like to introduce the general process of the Bitcoin transaction first. So as we all know, the Bitcoin is a public ledger system. And now, as shown in the figure, we assume that there are two parties. The Alice wants to send 6 coins to Bob. And since the Bitcoin is based on the UTXO models, so the Alice may have multiple accounts. So here we assume that there are 2 accounts. The first, A1, containing 3 coins, and the second, A2, containing 5 coins. So after the transactions, the previous two accounts are spent, the A1 and A2. And there are 2 new accounts that are generated. The first is the B1 here, containing 6 coins for the received values for Bob. And the second is the A3, containing the remaining coins for Alice. So what should be included in the transaction? So simply it's the input values A1, A2, and the output values A3 and B1. So how does the verify check this transaction? So since the Bitcoin is public ledger, the verify can simply access the information in the transaction, and he just check the 3, which can be summarized as 3 constraints. The first is that all the inputs and output values are valid, larger than 0, and the second is the balance, A1 plus A2 equals to A3 plus B1. Okay, and the third is that all the A1 and A2, the inputs accounts, are not spent before the transaction. So, so you can see from here there is a problem that since the transaction is public, so every user in the network can freely access the transaction. So they can know the privacy informations about Alice and Bob, and those inevitably poses threats to the privacy, right? So the researchers come up with the notion, the anonymous cryptocurrency, which require that we need to ensure the privacy of both the identities and the amounts in the transaction. So specifically, there are 2 targets. The first is called the confidentiality. So this is done by the confidential transaction, which includes the range proofs and the balance proofs. So here we need to hide the amount and allow the verification at the same time. So you can see from the figure, the transaction now only includes a range proofs for all the input and output values. And the verifier cannot read the exact amounts. So the verifier received the range proofs, and he can be convinced that all the amounts A1, A2, A3, B1 are larger than 0, and their balance are hold. But he cannot know the exact amounts. Okay. So the second target is called the anonymity. So in this work, we mainly focus on the ring signature, the technique to achieve the anonymity. So a ring signature can hide the identity of the real signer among a ring of members. Here, the Alice and C1, D1, E1 here. So now the transaction only includes a ring signature as well as a list of public keys. So for the verifier, he can check the signature and be convinced that one of the public key among the list has signed this transaction, but he cannot determine which one exactly. Okay, so although we have those constructions so far, there are still problems and challenges. So the first is that most of existing anonymous cryptocurrencies are not quantum secure, right? And to achieve the post-quantum secure, we take the lattice space as an example. There are some additional requirements. For example, the messages must be short under the sys problems. And as a result, we have to convert the large message. For example, the value, the amount, we need to convert them into small pieces before we using the lattice-based commitment scheme. So just the hashed message commitment here. And also there are some already lattice-based solutions proposed, but they are not efficient enough. So what's our object? So the main object is that we want to propose efficient and post-quantum ring-city protocols for the anonymous crypto, right? And it mainly contains 3 steps. The first is to build a balance proofs under the hashed message commitment. And the second is to propose a new relation for the linkable ring signatures. And the third is that based on the previous 2 techniques, we want to build a post-quantum ring-city protocol. So these results can bring us some benefits as well. Okay, so this is a quick overview of the ring-city construction in previous work. So you can see that the ring-city contains mainly 2 parts. The first, the confidential transaction, it's based on the balance and the range proofs, and further the range proofs is based on the binary proofs. And for the other part, the ring signature, it is built on a so-called the one out of many proofs. And it also is based on the binary proofs. So here in our work, we made some modification on the construction. So the first is that for the confidential transaction, the balance proofs, we reduce its relation to more efficient ones called the inner product relations. And for the range proofs, it's based on the binary proofs. We propose a partially amortization for the binary proofs to improve its efficiency. And for the third one, the ring signature, we found that the one out of many proofs is maybe too strong for the ring signatures. So we propose more simplified linear sum relations. So we start from the first part, the binary proofs. So okay, a binary relation is that the vector B should be binary. This can be reduced to an equation which is a Hadamard product between the binary vector B and the vector B minus the vector 1. And it should equal to a vector of 0. So previously there do exist some batching technique for multiple binary proofs, but it is not practical in ring-city because in ring-city we need to commit all the inputs and the outputs values separately, right? So for example, the previous work in metricity, to mint S accounts, the prover needs to run S binary proofs. And this will incur a large cost for the opening vectors. So our target is that can we adopt a similar of the so-called amortization technique. So first introduced in ACF 21. So the amortization technique allows the prover to prove that multiple witnesses under the same relation with the cost of only 1. Okay, so but unfortunately, the amortization in ACF 21 only supports a homomorphic relation. But you can see that our binary relations are not homomorphic. But there is still some space for our to improve. So for the committed binary relation, there are actually 2 constraints. The first is that the commitment on the binary vector B with the random vector R equals to a value B. And the second is the binary constraint, as we mentioned. So our idea is that we can apply the amortization partially on the first equation while leaving the second equation unchanged. So the prover can send the batched opening for the random vectors Ri, but the openings for Bi is sent separately. So actually concretely we can reduce the proof size to the half of the original one. And let's move on to the balance proof. Okay, so for the as we mentioned, for confidentiality, we need to apply range proofs and balance proofs to hide the input amounts. Here, the V1, V2, and the output amounts V3 and V4. Okay, and also we need to allow the verification on the amounts, that all the amounts are larger than 0 and the balance is holds. But as we mentioned, we try to apply some lattice-based commitment, the HMC here. So to use the HMC, we have to convert the value Vi into some short messages at first. So in previous work, they just convert the values Vi into the bit representations, right? So here the V3 equals to 10, and the bits of V3 equals to 0101. Okay, now to ensure the V3 is larger than 0, it is quite simple. We can simply apply the binary proof for it, right? But how to prove that the balance holds? The V1 plus V2 equals to V3. Okay, since we are doing the addition in the Q modulus Q field, right? So the addition between the bits is not correct. Here, the bits 3 plus bits 7 is not equal to bits 10. So how to solve this problem? Previous work uses some character values. Okay, you can regard it just as the carries, right? And they add the carries C, the vector C here, and make the equation holds, right? But this incurs another new problem. We introduce the new vector of the character values C. So what if the range of the C is invalid? So we need to instantiate some additional range proofs for C, and this will incur extra cost. Okay, so what our observation is that we do not need to check the equation for the bits representations. Instead, we can check the inner product relation. Okay, so you can see from the second line, V1 plus V2 equals to V3 is equivalent to the bits V1 plus bits V2 minus bits V3, and inner producted with a vector, the powers of 2. Right? So this should equal to a value of 0. Okay, so now we can use the inner product relation to prove the balance relation and do not need to introduce some character values. So although you can see that we still introduce some vector of C, but the range of the vector C is already ensured by the binary proofs for the input and output values. So we do not need to instantiate additional range proofs for C. Okay, so but there is a still problem we solved is that since we checked the inner product relation, we need to ensure the Fi and the inner product between Fi and the powers of 2 being short at the same time. So, okay, so we just need to some well designed on the masking values in the opening of F. And we present a so-called the cycling masking here, and due to the time limits, I just skip it. Okay, so the last part is the ring signature. So the ring signature is based on the one-auto many proofs, and similarly, the one-auto many proof also includes a witness as a binary vector, the delta here, right? So the delta only contains one of the bit 1, which indicates the position of the real signer in the user group in the ring. Okay, and for the prover, he only needs to prove that 3 constraints. The first is that delta is a binary vector, and second is delta only has 1 bit of 1. And third is that the inner product between the vector delta and the vector of public keys is a commitment to 0. It just a common practice. The commitment to 0 is actually means the commitment to the SK, to the secret key. Okay. So previous works just use the one out of many proof technique directly in the lattice-based RingCT. But we found that in the lattice settings, the binary proofs requires larger parameters than other parts in the one out of many proofs, and which results in the larger proof size. So our motivation is that can we remove the binary relations here? Okay. The answer is yes. It is mainly because we already use the lattice-based assumptions, right? So the cis assumption will already requires that all the messages is in a small range. So just use this fact, we can ensure the soundness error is already negligible. So we can remove the first constraint that the vector B is a binary vector and just let the prover to prove the remaining two parts. And this is called a linear sum relation. And we have presented the formal security proofs for this lemma in our work. Okay, but there is a still small problem that we have solved is that in previous one out of many proofs, we use the Kronecker, the binary vector delta, right? And there is some small optimizations which can reduce the proof size from the linear size to the logarithmic size. But now, if we relax the one out of many relation to the linear sum relation, can we still use these optimizations? Okay, so don't need to worry about that. We propose a so-called the unbalanced relation, where the prover runs with a stricter relation, just with respect to the delta, which is a binary vector. But the verifier can simply check a relaxed one, where it does not need to ensure the vector to be a binary one, just a vector in a small range. Okay, so finally, we build a lattice-based RingCT. And there are also some techniques, and I don't have time to introduce. I just compare the performance. So for the proof size, you can see that our work outperforms the previous schemes, right? And also the proving and verification time, it is significant, right? Improvement. And let me just draw a conclusion. Okay. So to build an anonymous cryptocurrency, we need to hide the amounts and identities. So what our contribution is that the first, the binary proofs, we just allow them to be partially amortized. And for the balance proofs and the range proofs, we remove the needs for the character values and just reduce it to a simple relation called the inner product relations. For the ring signatures, we remove the binary constraints in the one out of many proofs and reduce to some called the linear sum relations. And for the ring CT, we also propose combining the linkable ring signatures with the balance proofs, and we solve some maybe some soundness problems when combining them together by a new technique called the serial number check. Okay, so that's all of my presentations. Okay, thank you for your listening.
Yeah, thank you. Are there any questions? Okay, one quick question. So the tools that you present, they appear quite generic and might have many other applications beyond cryptocurrencies. So can you think of any, or is this, did I misunderstand this?
So the other applications, right? So in my perspective, I think for those ring signatures and just the binary proofs can be used to improve some the performance of such as the anonymous credential systems in Web3, and some others. It can also be used in the smart contracts of Ethereum, for example, the anonymous data, right? Okay. Right.
Okay, nice. Thank you very much. So let's thank the speaker again. And the next talk is about OCash, fully anonymous payments between blockchain light clients by Adam Bletchley Hansen, Jesper Boos Nielsen, and Mark Simkin. And Adam will give the talk.
Thank you. Yeah, this is joint work between myself, Jesper, and Mark. And let's get straight in. So first of all, anonymous transactions. There are lots of different constructions for these in the blockchain world, in lots of different flavors. But most of them, or as far as we can tell, basically all of them, assume that the person making the proofs or the person making the transactions has access to the full state of the blockchain. And in reality, if we want these kind of transactions to become something that you can use in your day-to-day life, then you need to be able to use them from what we call light clients. This could be your mobile phone or your laptop or some other low-performance device that doesn't have gigabit internet connections. So in reality, many people will be trying to make these transactions without access to the full state, and then they'll be querying full nodes that are running the blockchain to get the information they need to make their proofs. So the question we asked in this project was, can we make a provably secure anonymous transaction scheme which supports light clients with full privacy against these full nodes that they're talking to, and also provide strong anonymity guarantees, meaning that even the sender of the coin cannot see when it gets picked up by the receiver. So this is a very classic style of anonymous payment scheme. So you have Alice make some kind of coin or commitment and throws this into an accumulator on the chain. Then she sends some kind of opening information to Bob, and then Bob will do some kind of privacy-preserving way of showing that he knows some commitment on the chain and he gets the coin. And I'm not showing this to show that all schemes can be broken by this, but this is just to try and give an idea of why constructing these seem to be difficult. So if we move to the light client setting, now instead of Alice communicating directly with the blockchain and Bob communicating with the blockchain, they both talk to a server, which is not trusted and should not learn anything about the transaction that's happening. So what's the problem here? Let's try and walk through a very classic style of anonymous transaction. So Alice is going to make a commitment, and it's going to be from Alice to Bob with some randomness and some transaction identifier. Then she's going to post this onto the chain, where it's going to get put inside some kind of accumulator, maybe a Merkle tree. Then she's going to send the coin to Bob, which includes the randomness to open it and the transaction identifier, which until now is still private. Then Bob is going to use the randomness and the transaction identifier by announcing the transaction identifier and then making a proof that he knows some transaction in this accumulator, which with some randomness that he knows opens to this transaction identifier. And then the parties will check that this transaction identifier hasn't been used before and it gets burnt, so no one can spend this again, and Bob gains 1 coin. So the way that these kind of proofs generally look is you have this commitment, and then Bob will do some sort of NISIC that says, some non-interactive zero knowledge proof that says there exists some commitment in the Merkle tree, and this commitment includes TID, the transaction identifier, and it also includes me as the receiver, but I won't necessarily say who I am if I'm doing this anonymously. And I know the randomness to it, and TID has not been used before, which is easy to check in the clear. The problem in this scheme comes in step 1. So when I'm proving that something exists inside a Merkle tree, I normally do something like this. So say that my transaction identifier is label 3, then I would show all the other paths in the Merkle tree to prove that this exists in there by showing another path, and I would do this in zero knowledge. The problem is I don't know the state of the accumulator because I'm not running the blockchain. And to do that, I would need to know, what is this state, what is this state, what is this state? So what I would do is I would say, hey, full node, can you please send me this thing, and this thing, and then I'll give you a NISIC saying I know something in the accumulator. But that obviously leaks a lot of information. And in fact, in schemes like this, you really need to get all of the data blocks in the tree, because anything he doesn't send you, he knows could not have been your transaction. And this is very specific to this kind of scheme, but this idea of if I can make a payment without knowing everything that's on the blockchain, then the things that I don't know are clearly not in the anonymity set of the transactions that I could have be picking up. And this happens so we want this communication here to be able to give Bob the full anonymity set of all possible transactions against the full node, while ideally not having to download the entire state of the blockchain from the full node every time he wants to make a payment or receive a payment. So our contribution in this paper is modeling this problem in the UC framework. Then we propose a concrete scheme based on ORAM, which we believe solves this, and we prove its security in this framework. And along the way, we have several different building blocks that may be of independent interest, including a new re-randomizable encryption scheme, and what we call a strongly oblivious read once map, which is basically an ORAM that you can only read each element once and they never get reinserted. and then a few other things like the compressible randomness beacon. And I'm going to try and give an idea of how the scheme works and show a few of these components that may be interesting. So the idea behind our scheme is Bob is essentially trying to download or touch all of the possible information on the full node to make his proof. But the full node shouldn't learn anything about what it is he's touching. So the full node should see it as he reads everything. Bob only wants to read some specific things. So this sounds very similar to oblivious RAM. So we want to do an oblivious read of some subset of the data. There are other primitives that work here as well, like peer. But we chose to build something off path-ORAM, which I'll do a short introduction to now. And path-ORAM is an ORAM where you can do reads and writes in quite a very simple way with polylogarithmic overhead. So the way path-ORAM normally works is if I want to write something into the ORAM, I'll put it up into this bucket, and then I have a binary tree of splitting buckets. And then I also sample some random leaf at the bottom of this binary tree that it's going to travel towards. Then whenever the bucket starts getting full from adding more things into it, it'll slowly bubble down the tree. Each time this gets full, I'll split it into this and this based on which leaf is in each of the encryptions here, re-randomizing or re-encrypting each time. And it slowly gets towards the leaf, but if I want to read it at some point, then I just read this entire path. And because the server doesn't know which leaf this encryption is going to when it was inserted, this path essentially doesn't leak any information about what I'm reading. And then in an ORAM setting, what I would then do is after reading this, I would re-randomize or I would throw this back into the top, going down to a new leaf and then read it again next time. But in our setting, we only need to read once, so we just don't do that. So yeah, Bob needs to download enough state to prove it, and the way we do this is we have a trusted third party, which is later a committee, and I'll discuss this at the end, which is going to run a read-only ORAM of commitments. So all the commitments are going to get put into this ORAM structure, and then when Bob wants to read, he reads the one of the paths. So the way this works in our scheme is Alice will create this commitment, which is going to be an encryption under Bob's public key of our re-randomizable encryption scheme. And it's going to include an input to a leaf, a transaction identifier, which is what we burn to kill in the coin, and then the commitment itself. And I'll show what these are later. Then the committee will sample another random value from a random beacon on the chain. It'll use this to pick a leaf. And then it inserts C into the top of this ORAM structure with the target leaf as the thing it should go down towards. And then Alice will send the opening information, will send this commitment with this opening information to Bob, and also send one of the inputs of the leaf to Bob. Now some time will pass, other things go in, the committee will slowly maintain the ORAM structure and this will bubble down. And when Bob is ready to read, he will first request the crab key, which lets him see the full history of the random beacon efficiently. Then he will compute which leaf his transaction went down to, based on knowing which block it was in. And then he will just read this entire path out of the ORAM, which is logarithmic in the size of the number of total coins in the ORAM, and do an OR proof of all of this, that he knows one of the commitments, or the content of one of the commitments. So now what is the encryption scheme we're using here? We had some properties that we needed for this to work. So we needed it to be re-randomizable so that each time it moved in one of the buckets in the ORAM, the server could re-randomize it without knowing the private key that it was encrypted under. We also need key indistinguishability, because if you can track which key encrypted which thing, then you can clearly see who they're going to, and that also breaks it. And finally, we needed strong message binding so that each message can only be decrypted to one message regardless of what key you try and use, which was needed for some of the proofs. So this is the scheme we're using. We start by sampling a normal Elgamal style public key. And each party will have one of these. Then the way we do encryption is we make a 4-element tuple. So we have the generator and the public key both raised to some random value. And then the generator and the public key raised to a different random value where this one's multiplied by the message. And this looks a little bit weird, but basically what's happening is on the right-hand side, we just have an Elgamal ciphertext. And on the left-hand side, we have a sort of binding it to a specific public key. So you can sort of see the left side is what we need for some of our stuff, and this is just a normal ciphertext. Then when you decrypt, you first check that this matches your private key, this relation. And if it does, then you can invert this, multiply it on here, and then you get the output out. So this means that a decryption is only valid if the same private key that matches the first two together then decrypts the second two. And the re-randomization, which is what the server needs to do, is then what is the reason we have these two. So normally to re-randomize this kind of ciphertext, you would need to know the private key. because you can't just exponentiate C and D, because then you mess up the message completely. But what we can do here is we can take A and take B, raise them both to some random value, and multiply them on here. And this means that this will still be a valid, when you invert this and multiply on here, you'll also kill this term here. So this is still a valid Elgamal ciphertext. And then we also re-randomize this pair here. So all the invariants still hold after we randomize. We do as many times as we want. We're not changing anything. But it's now indistinguishable from like a completely separate ciphertext. And the way that these coins get equivalent, so this is the content of we have the G, the H, the G, the H, and the message here that's being encrypted, which is the transaction identifier, which is a Peterson commitment to the sender, the receiver, a nonce from the sender, which is needed for the proof to go through, and then the amount that you're sending in this transaction. So Bob will receive log n of these ciphertext pairs, and this is slightly wrong, he knows the secret key because it's his secret key, Alice is encrypted to it. But he can recognize which one is to him, and he can decrypt it and get the TID. And he publishes this TID along with a NISIC showing an all proof over all of the things in the branch he got from the server, that one of them is the correct matching thing. And a quick note, I'm not going to show all of the Sigma protocols because there's no time, but just to show how simple most of them are, if you take this and then you multiply the inverse of the TID on this side, you just got a public key relation, a public key relation. And then you can insert your own public key as a third relation, and you get three values where all of the things on the left side raised to your private key are the things on the right side. And this lets you do very efficient Sigma protocol proofs based on D-log stuff, which let you, there's the one out of many thing by Groth et al., which lets you do this logarithmic number of Sigma protocols and the number of elements in the branch. And then we also have Sigma protocols in the paper for when you send the transaction to the chain, you need to prove it's from you, and you have the balance to do so when you've lowered your balance, and likewise when you collect it, that your balance has gone up, that it was from you, etc. So now a quick note on the read once map. Initially, it looks a lot like you can just take the path ORAM and use it directly without having to worry about anything else and just not do the reinsertions. But this is actually a little bit dangerous because the security model of the ORAM is that everything is a ciphertext and the server doesn't know what anything is. So your adversary has no idea what any of the values are moving around. They all look random. In this setting, you could theoretically have a setting where you have 2 coins that are yours, and then every other coin is owned by the adversary. So this means the adversary can decrypt all but 2 values in the entire ORAM structure, and you still need him to not be able to distinguish which of these 2 coins is which. So we had to make a different security game here, which was based on the adversary choosing some number of coins, we choose some number of coins, and he can't have any advantage even in that setting when he can track his own coins through the structure. How's the time? 5 minutes, okay. And then a very quick thing, so this crap key that I mentioned before, this is what we call the compressed random beacon. And the goal of this is that we have a source of randomness on chain, which will be releasing a new nonce every time someone puts a coin in. And then Bob clearly can't ask, hey, what was the value of this at this point here? Because that would leak information. So we've designed this key from like punctural GRM PRFs, where you can give the current state, and that will allow you to evaluate all previous states without any blow up based on how far back you're going. And all the other versions of these sort of reversible randomness beacons, if you had to go a very long way back, the amount of time it took started scaling. So that was also a nice contribution that we thought was cool. And then finally, strong anonymity. So clearly, if I tell you what the TID is, I'm breaking strong anonymity because Alice also knew what the TID is. So for strong anonymity, instead of revealing the TID, we reveal this like oblivious hidden identifier, and we add this extra term into the encryption or into the coin. And then what we reveal is a PRF run on this. This is very similar to what a lot of other anonymous transaction schemes do. So we're basically reading a PRF run under our key of the identifier, so it'll still be unique because this is deterministic PRF. But yeah, we show you the anonymity. And this obviously requires all of the proofs to be made slightly more complicated, more terms added everywhere. But I thought it's easier to show the simple version. So the final discussion is the committee. So it's a very big claim to say that we have a trusted third party managing all of our things for us. That would make mixing very easy. But we think that in this specific case, this isn't too unreasonable a thing to do. So the first thing to note is that this is quite a very easy, maintaining this ORAM is quite easy to make verifiable. And we have some demonstrations of how you can prove that each of the update steps it makes is correct. And if it's verifiable, then the only thing that the adversary can do in this case is break privacy by revealing which leafs things are going to. So they can't print money in this if you have a verifiable SORM running. And even if it deadlocks and dies, no money is lost because the clients can always go look at the back to the block where it was first inserted and just claim it from there. So there's no risk of losing money either. And for example, a lot of proof-of-stake blockchains already have these very large committees sampled. So if you have a verifiable MPC version of a protocol like this, you can run that in the committee. And they can then you know that everything is happening as it should, because none of them will learn anything unless you compromise all of them, and then the blockchain is already broken. And the other interesting thing is this is a heavy assumption, but this is a necessary assumption, because our initial goal was to try and find where the lower bound was. And the more we looked, the more it felt like you really do need someone to have some kind of secret state managing this whole system to be able to make these kind of like sublinear light client protocols work. So if anyone has an idea of how to do this without needing someone running the secret state, I would love to talk to you because it's really interesting and we could not see a way of doing it. And yeah, there's some other directions that were looking at and are looking at. So there's obviously peer is another way of doing this that would be quite simple. There's also efficient ways of implementing this ORAM. And then there's also the other part of it, which is the recursive Stark and Snark style constructions of anonymous payments, which is a completely different model. So we're not entirely sure what stuff is like there, but you open yourself up to a lot of very nasty things like long-range attacks with expired keys and different things there if you're not very careful. But you also don't want to be binding yourself too tightly to narrow timeframes because that damages your anonymity set. But I think there's a lot of interesting directions from this, and given that the future of these, if we want them to become widespread, is that you need to be able to make these payments without running a full node. This is an interesting problem to look at. So yeah, thank you for listening. The full paper is on ePrint and a lot more details.
Thank you. Do we have questions? So everyone's still tired. So suppose I wanted to run your protocols on an existing cryptocurrency, such as Ethereum, for example. Yeah? Some of the building blocks I think you could probably implement in the Turing complete scripting language of Ethereum. Some probably not, such as the ORAM. Is that true? So what would be the extensions that one would need?
Yeah, I think the ORAM is something that's run completely off-chain by a group of people. This wouldn't be too unlike what some of the layer 2 solutions are already doing, where they're running their own stuff and then linking it back onto the chain. I think most of the other stuff should be very straightforward. All of our proofs are just pretty simple Sigma protocols on discrete log, so I don't see anything that would be too difficult there.
Okay, cool. Yeah. Thank you very much. Then let's thank the speaker again. So now we have Hamza Abuzallah on graphs of incremental proofs of sequential work. just keep talking. It's, yeah.
Okay. If I knew so many people would attend, I would have tried harder for my slides, but try my best. Very happy that there are so many people around. So welcome to my talk. So don't be scared if you don't know what incremental proofs of sequential work schemes are. I'm going to explain at least the base clearly, and we'll go slowly. Anyway, so the outline of my talk, I will talk first about proofs of sequential work schemes. I'll give you a definition and an example construction. And then I will take the pen in defining incremental POWs and motivate them. So this will take some time actually to do well. And then I will highlight the main results without giving too much, because otherwise I will need more time and I will get you lost. And I will end up with a very intriguing open problem that I think nobody cares about, but it's a fantastic one. I do care about. Okay, so So because part of this work is definitional, fixing some definitions in previous work, I will have to be somewhat rigorous. So the definitions will be in the parallel random oracle model. So all of you know this. So we have a random oracle tau, and you have an unbounded adversary that has oracle access to tau, and it has an initial state is 0. And it proceeds in rounds. In each round, in the ith round, it can send parallel queries to the random oracle, this set of queries, and it would receive the response. Okay, so the oracle evaluated on them. And the measures that I care about is the time of this adversary or of this algorithm is n, is the number of rounds, and its space complexity is the maximum space during these rounds. Okay. Okay, just to set this clear. And at some point, I will also need to care about the total number of queries that this adversary asked during its interaction with the oracle. POSWs were introduced by Mahmoudi, Moran, and Badan. They're interactive proof systems. Okay, I think I need to see the slides from a distance. So they're interactive proof systems in which completeness says that the honest prover convinces the verifier. And efficiency is key here, is that the prover runs in time n, produces a proof, a succinct proof, and the verifier is very efficient. If we drop this efficiency requirement, everything is trivial. And the most important aspect is obviously soundness. And here, as a malicious prover, we'll say an alpha q epsilon soundness means if you have a malicious prover that makes a total of q queries to its oracle, and it runs in time alpha n, think of alpha as it's a constant less than 1, say 0.9n, and it makes v except with probability epsilon. I will show you what kind of values we can get in a moment. So this is soundness. Essentially, it says what you would like to have. If you don't run in time n, then you're gonna fail with a very large probability. So all proofs of sequential work schemes are graph labeling. And how do these schemes work? So the scheme is parameterized by a graph, say on n+1 vertices. And the verifier sends a Hyman entropy chi to the prover. The prover uses chi to solve the random oracle, and it computes a labeling of a graph, of the graph in question. The labeling is very easy. The label of the node is the label of its parents concatenated with the index. Okay, it's just you take the parents, you hash them together, and you get the label. So you label the graph, you send the sync, which we assume that is a unique sync here, and this will serve like the commitment to the labeling of the graph. And then the protocol runs interactively in a challenge response phase. The verifier will send some vertex, and the prover will have to respond with some labels. And it is important for these graph labeling POSWs that these responses are labels of the graph. There are no other things. The only thing that R's contain are a bunch of labels from the graph. And that's why we call these graph labeling POSWs. This syntax would be very important to prove the impossibility result that I will talk about. So we always assume that this is the structure. All the prover sends during the protocol are just labels, nothing else. Good. To give you an example, and I'm obviously very subjective, I'm choosing my examples carefully because I also have the slides. And I like this example because it's very symmetric and nice. Who doesn't like symmetry? So the protocol, so this is the graph, and the labeling we calculated it, and then the prover will send the label of the sync to the verifier, which commits to the labeling of the entire graph. And then the verifier will send challenge, okay, I13. So in this protocol, the prover has to respond as follows. It will have to find the shortest path that goes through 13 from the source to the sync through 13. And this is illustrated in blue. And on top of that, it will also choose the parents of this path, and it will send everything to the verifier. The verifier will do a natural consistency check, and everything is good. We know that the prover is doing well, and we do this t times. And then if everything checks out, the verifier will accept. this is a very small example. You can see for each challenge, you almost send the entire graph. But I have to remind you that the shortest path in a graph of n vertices is logarithmic, and the n degree of the graph is logarithmic, so the proof size is log square. So it's still bully log. Okay? So this is clear that completeness and efficiency are satisfied, and just to give you a flavor of these variables, alpha q epsilon soundness, you will get something like this. Epsilon will be related to alpha to the t, how many times you repeat this protocol, plus something related to finding collisions in the random oracle. Okay? And all schemes have the similar bound. Okay. So this is a BOSW. And now we would like to motivate incremental BOSWs. So let's look at the space efficiency of known BOSWs. All BOSWs, all schemes, the prover has two strategies to interact with the verifier. The first strategy is that it labels the graph and stores all the labels. Okay? And then it stores all the labels, and whenever in the challenge response phase, it always looks up the labels that it needs to respond to, and it does not do extra work. The other strategy is that, well, it labels the graph, sends the sync to the verifier, so it stores nothing, and whenever it needs to respond to the verifier, it recomputes whatever is needed. In the worst case, it could recompute everything. Okay? Of course, these strategies, the first strategy is great in terms of time. You do sequential time, you run in time n, but you have to store everything, a large space. Okay, this could be a terabyte of data. It's a lot of space. In the second strategy, you store almost nothing, but you have to, in the worst case, to run in time 2n, to relabel the graph again. Okay, so this is a factor of 2. And the space, well, it depends. It depends on the scheme. In some schemes, you can afford running in 2n. The space could be low, but this depends really on the scheme. So this is kind of before incremental proofs of sequential work schemes were introduced. This is what we know. But also for some schemes, we have some intermediate strategies. So for these two schemes, which I will, this is the one I showed you before, the skipless, and this is the CP, which I will show you its graph in a bit. You can store S labels. After that, you compute the labeling and you store only S labels, and you additionally compute N over S labels to respond to the verifier. So what does that mean? For example, concretely, you can run in time, say, n plus square root of n and space square root of n. Okay? And the question that motivates incremental BOSWs is that, can we get the best of both worlds? Can the prover run in time n, exactly n, and at no point in time it has more than bully log space? Okay? And the question is yes, and this is why you need IPOSWs. These are introduced by Dotling, Lai, Malavolta. And these are, I should say, the BOSWs that I introduced before, they're all interactive, and then you make them non-interactive in the random oracle model. These IBOSWs are defined non-interactively right away, and they have 3 algorithms, the prover, verifier, and incrementing algorithm. We require that the PV is space-efficient and tight BOSW. Tight is the relates to the time, and space efficiency what it is. So this is the time runs in n, and space bully log n, and as before, the proof size is small, and the time of the verifier is also small. And now we have the extra algorithm, the incrementation algorithm. The incrementation algorithm for n0, n1 that sum to n, if you get the incrementer a proof with respect to n0, then the incrementer would be able to generate an accepting proof for pi n, and it does so in time essentially in 1. Okay, so it receives a proof for, say, 1 year, and it want to compute for another year, and the computation time is just related to the incrementation. And the space is, as before, is efficient. And this you can do as many times as you want. And if we do not insist on the proof size, this becomes trivial. You can just concatenate things. So this is a non-trivial notion. What I want to say about this definition is that, so So the original definition and subsequent work really did not mention space efficiency at all. And if you don't mention space efficiency at all, as I show in the paper, you will have some trivial constructions. Some POW standalone, they actually achieve incrementality, which is not what you want. So we have to actually be careful in defining these things. And the blue stuff I added, and I argue in the paper that you actually need them for a meaningful definition. Okay. So now we have everything set up to talk about what we really want to talk about, is that if we look at the literature, and I'm mentioning things from reverse chronological order, so we have different sorts of graphs for POWs. We have this first graph that I showed you. It was introduced in this work and some other work later. And there is the brilliant CP graph, which looks like a Merkle tree with these extra funny edges. And then you have the original scheme by Mahmoudi Moran Vadan that uses highly depth robust graphs. Okay, so these are the only three graphs that we know for POWs. And of course, there's some other work. We did adapt this somehow and added extra edges for applications related to light clients in blockchains. So, but morally speaking, we have only these two graphs and this one. Okay, good. What about graphs of IPOWs? They're the same. This is the same graph was made into an incremental POW with Valerio, and this one, the original construction of DLM, that took the CP graph and made it into an incremental POW. The natural question is okay, and before the natural questions, both schemes use the very clever on-the-fly / incremental sampling technique introduced by Dotling-Lai and Malavolta. Okay, so incremental POWs are transformations of existing POWs. This was transformed. The natural question is, what happens to MMV? Why nobody's interested in this original scheme? So this is the main thrust, the main question that started this work. Can we transform MMV into an IPOW? Why isn't it transformed? And the second question, can we generalize these two schemes in one grand scheme? Because if you look deeply into them, the graphs are different, but they're morally the same. They're really very, very similar. And in this work, the answer is that we answer the first question in no. We prove that this is impossible. You cannot transform MMV. And the highlight, I wouldn't go into details into this, but the highlight is, this is how we do it. We first define what we call incremental graphs, and we show that IPOWs have incremental graphs. They are necessary for IPOWs. And we prove this very simply by relying on the efficiency requirements of INC. Okay? It's very simple to prove that. And the next step, we show that depth robust graphs are not incremental. And we show this by two steps. We show that these incremental graphs that we just defined, they have small space bubbling complexity. If you don't know what bubbling is, let's just ignore it. These are combinatorial games played on graphs to be able to talk about the graph structure rather than the labeling and the computation on the graph. So these incremental graphs have low bubbling, and depth robust graphs are known to have very high space bubbling complexity. And Mahmoudi uses depth robust graphs, and then we conclude that these graphs are not incremental. Okay, so this is how the impossibility result goes. It's very simple. I must say it's embarrassingly simple once you use the right tools. These are the tools that are used in the memory hard functions literature and proofs of space stuff. But once you adapt them and use them for POWs, it's very natural and it's very easy actually to prove this result. The second result is the generalization. We generalize existing schemes relying on these incremental graphs, and additionally a very mild syntactic condition on graphs called dynamic graphs. So this is essentially shows that these graphs are sufficient and necessary for IPOWs. And this is nice because we have just essentially one unified construction, and we get some corollary for the scheme that I showed you with extra edges. So just to give you a taste of like what are these graphs, because this sounds suspicious, an extra assumption, you would like not to have it, but this is really very mild and syntactic. Dynamic graphs are just very simply defined. Here I'm just not formally defining them. So think that you have graph index at G0. Then you build G1 from G0 as follows. You have a shifted version of G0, and you add some extra edges from the left to the right, okay, arbitrarily. And this is how you create G1, and you create G2 in the same way. If your graph can be described as such, this is what we call dynamic graphs. And it's easy to show that all known graphs are actually dynamic, and it's very natural. And then in the BEB, I also just generalized this cartoonish example to allow extra edges and extra vertices and extra edges, but it's very natural and simple. And these dynamic graphs are really, without having dynamic graphs, the incremental sampling technique would become a mess. So they're really very friendly to the technique that is used to transform POSWs into IPOSWs, and it's very minor, as you can see. The more interesting one is about incremental graphs. What are these? These are very, very simple to define. Take GI as a graph, and some bubbles that I showed here in gray, and some vertices. Think of these bubbles are the labels of the proof, of the POSW proof. Then a graph is incremental if you can bubble GI plus 1, the entire graph, can be bubbled in these complexities, which I did not formally define. This is the time complexity. It takes you time, essentially, not essentially, it takes you time. This is the time that you need to bubble the entire graph, and you can do it with low space. Let's look at it again. So this shows with these bubbles, you will need time only related to this part to be able to bubble the entire graph, because you may need to bubble the entire graph to respond to proofs that are related to GI plus 1. If you look at actual schemes, this is too strong a requirement. They work in a much more primitive way, in the sense that you don't really need to bubble anything in GI. All what you need to be able is to bubble this. But if you define it in that narrowly, then you wouldn't be able to prove the necessity assumption. So this is kind of what turns out to be the right definition for the tool. So to conclude, so in this work, I generalized IPOSWs relying on dynamic graphs and incremental graphs. And most importantly, we proved that MMV cannot be made incremental. The intriguing open problem is the following. So in here, I did not, the incremental graphs takes a POSW graph and asked how to make it incremental. While the main question is that what makes a graph good for POSWs? Like, what are the combinatorial properties that a graph has to have in order to be a good POSW graph? We have no idea. We know that these three graphs that I showed you before, these two graphs, and yes, these two graphs and this one, they all work. They all look similar, different. But we don't really know why they work. It's a very annoying thing. We would like to understand the necessary conditions on these graphs to be able to describe it combinatorially and say, okay, if the graph, any POSW graph must have these properties, and even better if you can also give sufficient conditions. As far as I know, this is a question that is open. Some people thought about it. I don't know what implications it may have, but it will give us some basic understanding of these problems. And thank you very much.
Thank you. So, time for a quick question. So you said that you don't really understand why these particular graphs work. But I mean, somehow the authors originally must have, including you, must have come up with that. I mean, this is like they got up in the morning, drew some random graphs, and so, oh, this works, or is there some more, clever insight behind this?
Good question. Let me, okay, so the first graph of the depth robust graphs, it actually makes sense because these are graphs that are dense in long paths. Okay, so it's kind of, they're by definition, they have lots of long paths, and then you cannot really cheat. But they were shown to be an overkill for the sequentiality, but they were. But then we came up, okay, so this graph came first, and the insight of this graph was, In the initial work, you take a dipterabus graph, you label it, and then you Merkle tree commit to it. And so what these clever people did is that they started with the Merkle tree commitment and embedded a very long path that goes through the entire graph. So they started with the commitment and the openings, and then they planted a very long path that goes through everything. And then that was a good intuition, and then they proved it. What we did here, we were inspired by actually something by non-interactive proofs of sequential work, proofs of work in a blockchain, where they were doing this skip list to kind of verify quickly that the blockchain is a blockchain. And we thought, okay, we can actually force the structure and build in without being randomized, and maybe we can actually prove that this chain is actually a chain by skipping things every now and then. So we also started with a very long path and made it friendly to local checking, and it works. But this is not satisfactory. We still want to understand why these graphs work.
Okay, yeah, thank you very much. So let's thank the speaker again. Okay, now we actually have a merged talk, but the speakers decided to overrule this and give two separate, shorter talks. And the first one will be given by Chelsea. It's about stateless and two-round threshold Schnorr signatures.
Okay, let me just, nope, other direction? Yes, okay. Cool, yeah, so thank you all for being here. I do want to say all of the background in this talk is relevant to the next talk, so it is a little bit merged, but not entirely. So today I'm going to tell you about a new scheme that is a stateless and two-round threshold Schnorr signature. Just to recap, I know we've talked a lot about threshold schemes, but just as a very quick summary, basically what we have for a threshold signature is a public key scheme where the secret key is split among a set of parties, and then you have one public key that represents the group. And generally we have n parties, but t parties are required in order to sign. And the scheme is secure up to t-1 corruptions. And for key generation, we can do key generation either via a trusted dealer or from a distributed key generation scheme. And then, so one reason why threshold schemes are appealing is because signing can be done without revealing secret keys to other parties. So basically all the secret computation is done locally. When we talk about unforgeability or security of a threshold scheme, it's very similar to single party signing, but the main difference is that at the beginning of the experiment, the adversary receives secret keys for all the corrupted parties. So here the adversary is able to denote which parties are corrupt, and then it receives those secret key shares. Here I'm showing the static setting. In adaptive security, the main difference is that the adversary can corrupt parties throughout the experiment. But with static, basically they receive secret keys at the very beginning. And so really the core difference when you're proving security is that the adversary is allowed to participate as a signer. So with multi-party schemes, and especially with multi-party Schnorr signature schemes, there's really two main questions, and these two questions and how they're answered distinguish all of the schemes in the literature. So when you see different types of schemes, they really differ in these two components, which is how the nonce R is shared and then how the secret key is shared. So really the variations just kind of come down to these two questions. So to kind of recap where we are in the literature, this is a little outdated, but because new schemes come out all the time, but this is kind of the core randomized schemes. So in the literature today, the core randomized schemes really come down to 3 and 2 rounds, where the 2-round schemes are secure under interactive assumptions, mainly AOM, or here this shows OMDL, but it's also under the algebraic one more discrete log problem. And then 3-round schemes are secure under discrete log. So this is really kind of the core differentiation between the schemes in the literature. So, so for these efficient schemes, they all are concurrently secure, which is better than schemes, I guess, prior to 2020. And then, but the problem is that they're randomized. So what this means practically is that for signers, when they're performing signing in these multi-round settings, all of the secret information for the nonces that they generate in the first round needs to be kept locally and then retrieved in the second round. So yeah, that can be problematic for implementations. Yeah, and here I'm showing just honest minority schemes. So yeah, so really the motivation for deterministic schemes kind of comes down to that fact. So yeah, so randomized multi-party schemes require state keeping. And practically this really comes down to like maintaining a database with a lock and then making sure, especially because you can't reuse nonces, that those nonces that are used are then deleted, and that can be kind of problematic when you have nodes that can go online and offline. So, and yeah, because it's Schnorr, if you reuse a nonce, if state is reused, then there's a key recovery attack and like with two signatures that have been issued. And maybe if you're an adversary, you can force a node to go offline, and if nodes don't recover properly, then this can result in like real problems. Yeah, and so then you get into implementation complexity like locks and careful deletion. So here when I'm talking about a deterministic scheme, this is really a means to a goal. And so the goal here is statelessness. So the means is having a deterministic scheme, but the goal overall is to have a stateless multi-round signature scheme. So yeah, so I showed you a Schnorr signature before, but I'm going to like really, really briefly re-show it to you. So yeah, for a single party Schnorr signature, we just have a discrete log key pair. And then for signing the message, we sample a nonce at random, we generate the commitment. The challenge is just the hash of the public key message and commitment, and then you have your response, which is just a zero knowledge proof of knowledge. And then verification all happens in the exponent to check that linear relation. One thing I want to point out is the difference between Schnorr and EDDSA. So EDDSA is actually used in practice. But the main difference with EDDSA is that the nonce is derived from the hash of the message in secret key. So this is actually used to prevent issues of bad randomness. But something you might ask is like, oh, well, why can't you actually derive the nonce in Schnorr in this kind of way? So if you were to be able to derive the nonce in this kind of way, you would have a very simple deterministic scheme. But yeah, this is something you cannot do, because if you were to do this naively, it's very, very insecure. And there's a recovery attack in just basically 2 signing rounds. And the main issue is that it's not publicly verifiable. So your honest parties might be able to follow those steps honestly, but your adversary could derive their nonce just randomly, and you wouldn't be able to verify that the dishonest party followed the protocol. And if the dishonest party can do that, basically if all the honest parties derive their nonces in this way, but the dishonest party just sampled their nonce at random, what they would be able to do is they'd be able to change the group commitment big R, which would change the challenge, but all of the honest parties' nonces would remain the same. Okay? So it basically just comes down to a very trivial nonce reuse attack. Okay, so yeah, basically what we want is that all parties can prove that they generated their nonces honestly, and prior approaches in the literature just use generic snarks or generic MPC. Those are kind of the 2 main approaches in the literature. And really the goal of this work that we wanted to do was to define a simple and efficient deterministic threshold Schnorr scheme. So we wanted to kind of go away from those approaches and design something that was simpler, that would be kind of easy to implement. And so yeah, so we were able to do that, and we introduced a scheme called Arctic, which is kind of fun to talk about in Norway. So yeah, basically it is a stateless threshold scheme, but there are trade-offs. So it's 2 rounds, which is nice. It doesn't require generic MPC or snarks, but we do require the assumption of honest majority. So that's the main trade-off here. And what that means is that we require at minimum 2 T-1 signers, and then the adversary can still corrupt up to T-1. Yeah. And it is efficient, but only for moderately sized groups, so really for groups less than 25. So if you're doing small signing sets, but where you can support honest majority, then this is a good scheme. And so I'll show you the scheme really briefly. So basically what we do, we generate, so for key generation, we generate all of the Shamir secret shares, and then we generate what we call verifiable pseudorandom secret sharing keys, which I'll discuss next. So basically there's two secret keys that are derived. And to sign, we use this verifiable pseudorandom secret sharing construction with those respective keys to generate the nonce in the commitment. And for the second signing round, we verify that everyone has generated their commitment correctly. If they have, then we rederive the nonce and commitment. And then the group commitment is just the product of all the parties' commitments with the Lagrange coefficient. And then signing is very similar to other threshold Schnorr signature schemes. And we use a similar combine algorithm as well, where it's just a linear combination of all the signatures. Okay, so yeah, so basically correctness comes down to the fact that we can interpolate the nonces effectively using Shamir secret sharing, and then similar for all of the secret signing keys. So correctness holds with respect to Shamir secret sharing. Okay, so I showed you this VPSS building block. Basically, you can think of this as a secret shared PRF, and under the hood, it builds on an existing pseudorandom secret sharing scheme by Kramer et al., but with an additional verify algorithm. And we actually saw this same building block, I think 2 days ago, with the lattice, I think it was a lattice threshold signature scheme. So they use the same building block as well. So it's kind of nice to see that it pops up in different places. And basically, in addition, what we do, so we use this pseudorandom secret sharing scheme, but then we define a verification step, and that just ensures all parties follow the protocol. So yeah, just to kind of remind you, replicated secret sharing, what you do is every party has a set of shares where they lack exactly one share in order to recover the threshold. So basically, you just have sets of sets, and when parties sign, they take whatever corresponding share is for that particular set. So you're essentially doing like repetitions of additive secret sharing, but with respect to all of the subsets. Okay, so yeah, basically under the hood, what we're doing is we're hashing all of the respective shares for each particular subset, and then we can interpolate them into a particular nonce. And then basically to derive the joint nonce, you do Lagrange interpolation to the constant term of an unknown polynomial. So it's kind of under the hood how pseudorandom secret sharing works, where the core component is replicated secret sharing. Okay, so yeah, so we were able to prove that Arctic is unforgeable with respect to the discrete log problem, which is nice, in the random oracle model, but under the assumption of honest majority. And we actually do implement the scheme and we show benchmarks. So we were able to show benchmarks with respect to a scheme called MuSig-DN, which uses bullet proofs. And we can see that up to about 25 parties, Arctic is faster, and then the crossover point happens with about 25 parties. But we also see that the scheme parallelizes quite well. So as you add parallelization, then the scheme is able to scale. So yeah, overall, we do think statelessness is desirable, and we introduce a scheme called Arctic, which is a stateless scheme. It builds on pseudorandom secret sharing, which we saw before, but it does require honest majority, but it's efficient for small signing sets. And that's all. Thank you.
Thank you. So we are very tight on time, but I hope Tiran doesn't hate me when I say no. We can maybe ask one quick question or so. I thought this makes more sense, right, after the talk, yeah. So is there any question? Okay, then we
Great.
take them offline or
Okay.
ask them later.
Sounds
Okay.
good.
The final talk of the session at the conference is about stateless deterministic multi-party EDDSA signatures with low communication by Qifeng, Kang Wang, Kai Zheng, Xiao Wang, Yu Yu, and Zhang Ji. And Qi will give the talk.
Okay, thank you. Let me show another work on the stateless deterministic threshold snore. Okay, this paper is solving this problem by designing a cryptography protocol that makes sure each party can prove the public nouns, for example, the capital RA and the capital RB, is honestly and deterministically derived by the pseudorandom function with the paper seed and the signing message. This is clear by definition. So the core challenge is to construct such box that has each party to produce the authenticated paper seed in the K generation, and subsequently they can prove in their knowledge proof on the comparison seed circuit of pseudorandom function and the circuit G. Okay, we first prove the Boolean circuit of the pseudorandom function with an MPC-based proof systems. And as for the second part, we design an information theoretical map over the group that compacts the Boolean circuit and the exponentiation or the elliptic curve operation. Okay, firstly, we extend the information theoretical map to the multi-verifier setting, which means the prover need to the prover who knows the secret value x will construct a pair of max with each verifiers. The difference from the pairwise max is the prover need to keep the same x value. Okay, so given the authenticated secretly shared x, we let all parties to evaluate the Boolean circuit with that x value. So for each gate, if add gate, it obviously can be evaluated locally, and if multiple gate, since the prover know all the plain text, for example, the omega alpha and omega beta, it can send the difference between the real product and the random value to the verifiers, and then all parties can compute the authenticated value of the product with a linear operation. This is simultaneous execution. So finally, we check the Boolean circuit with a batch protocol in the multi-verifier setting, which takes all the input, all the multiplication tables of and output the result, whether the multiplications are computed correctly. So let's see the batching. We apply the polynomial batching protocol inspired by mac and cheese. This idea is began by the verifiers send random challenges to the prover, and they randomize the multiplication tables and check the aggregate product Z. Okay, we let the prover run all the inputs to polynomials of degree 1, and they can construct an inner product of these polynomials. So we get a polynomials of degree 2 with 1 point at 2 point well equals to the product Z, which can be easily verified by the check zero subroutine. Okay, now let's verify point random values, a random point of the polynomials, and recursively checking. So if all checks are accepted, the verifiers can trust the Boolean circuit of the pseudorandom function is honestly computed. So the question is how to deterministic. So instead of sampling random challenges, we let the parties generate challenges using the Fair-Shamir heuristic. Okay, we use random authenticated random value for each multiplication gates. So we apply the PCI function to derive them. Basically, the PCI function can deterministically incremental and on-demand local generation of correlations with a pair of short keys. So we prove the first part with communication course of T in one round. Okay, let's see the second part. In this part, we need to prove the circuit G, which is the exponentiation or elliptical multiplication. So we still extended the information theoretical map to the group. It's all the same, except the operations are performed over the group and the integer operations are performed modular of the order Q. So after we evaluate the Boolean circuit, we get the authenticated capital R, and multiply by the generator G, we get the authenticated capital R, which can be easily verified by the opening and checking the max on the capital R. But seems fine, but it actually doesn't work. This is because the output of the Boolean circuit are bit values over the binary extension field, which cannot be directly aggregated to some value in over the group G or over the integer ring. So we apply a conversion from the binary extension field to the integer ring, and multiply the converted little r with the generator G to get the authenticated capital R. As for the conversion protocol, we apply the EDA bits. This is a classical idea for the conversion, but we make a few differences. The first, we extend the on-demand EDA bits using PCF function, and we apply sacrifice-based consistent check because we just need one EDA bits for each signature. Okay, so we construct such box with communication cost of O of T hard plus kappa times of L, which is the length of little r. Okay, the communication cost round is still a single round, and the security is directly follows from the PCI function and the information theoretical map. So a short summary, we propose a stateless and deterministic multi-party IDSA signature. Our assumption is all but one malicious corruption. Okay, our technical supports standard IDSA PR function, and the communication cards is improved compared to previous works, and the communication rounds match the regular threshold store. Okay, this is a short introduction of our work. Thank you.
Thank you. Any questions? So it's like in my class, right? If I say at the end is approaching, then nobody wants to ask anything. I would like to ask something to both speakers, actually, just very quickly. So Schnorr signatures are seemingly very difficult to prove tightly secure or with good concrete security. Then you have a multi-user setting with corruptions, which makes this even more difficult. So can you say a few words about concrete security, not only in your constructions, but actually in this overall area? So I guess this sounds like a very difficult topic in that context. Is that true?
Is this back on? Yeah. Yeah, I mean, I think there's impossibility results about Schnorr being tightly secure. So those same results carry on over to this. The loss, yeah, I'm trying to think. That's a very specific question about our proof. I think the extra loss is not too bad. It normally comes down to like querying a hash function before you're able to program. So yeah, I think the extra loss is not too bad in our case. But
Thank you.
I think it's different for applications. If you need more security, you can choose the one, and if you need more practical, you can choose another. It's different choice.
Okay. Good. Yeah. Let's thank both speakers again. And this concludes then the technical part of the conference. So I would like to briefly take this opportunity to say thanks to everyone for the very pleasant experience that this conference has been. Thank you, Justin. It was a lot of fun to work with you. Yeah, exciting, but yeah, I guess thanks for the really pleasant experience. And then I think the general chairs also will have some concluding remarks.
Do you want to go first? Yeah, so we also want to thank everyone for both submitting papers and attending the conference and making it a great conference together. I think we've tried to prove a framework for the conference, but you know, it's all about the content and the people showing up. I hope that you enjoyed the venue and the way we organized it, and at least from a personal note, I really like these kind of conferences, you know, compared to having an airport hotel or something like that. So if you know of a cool place in your local area, I would really encourage people to reach out to Julian and the PKC steering committee and offer to organize PKC in the future and to make a similar event like this where people can go and explore and enjoy a nice area. And I think that's it from my side.
We also would like to thank our volunteers from the crypto group at NTNU who helped us, and all the session chairs who also helped making this conference run so smoothly. Thank you all.
And finally, the conference ends with a conference lunch. So please head over to the lunchroom. And also the bus will, as I mentioned, leave at 1:15. So those of you joining the bus, make sure that you're in the reception area a few minutes before that. Okay, thank you.